Every time you look out of an airplane window, it feels like you're already as high as you can possibly go. The clouds are far below you. The sky above starts turning darker, almost black. The world feels distant, quiet, almost unreal, and naturally a simple question comes to mind. Why stop here? If flying high is more efficient, if the air is smoother, if there's less traffic, then why don't airliners just go higher? Why not 50,000 feet or 60,000? Why not push all the way to the edge of space? Because at a certain point, the sky stops helping you and starts working against you. There's an invisible boundary up there, not a line you can see, but a limit defined by physics itself. A point where flying becomes less efficient, more dangerous, and eventually impossible for a commercial aircraft. And that limit sits right around 40,000 feet. To understand why, you have to start with something simple: air. Because everything an airplane does, every bit of lift, every bit of thrust, every bit of control depends on air. At lower altitudes, the air is dense, thick, full of molecules. That's good for lift, because wings rely on air flowing over them to generate upward force. But it's also bad, because dense air creates drag. It resists motion. It slows the aircraft down and forces the engines to burn more fuel. So naturally, aircraft climb higher. Higher altitude means thinner air, less drag, better fuel efficiency. That's why commercial jets don't fly at 10,000 feet. They climb to 30,000, 35,000, even 40,000 feet. Because up there the balance is better, less resistance, smoother air, more efficient flight. But then something starts to change. As altitude increases, air doesn't just get thinner, it gets too thin. And when that happens, the very thing that helps the aircraft fly begins to disappear. Lift starts to become a problem because lift depends on air density. The thinner the air, the less lift the wings can generate at a given speed. So to compensate, the aircraft has to fly faster. Faster airspeed means more airflow over the wings, which helps maintain lift. But this introduces a new problem because aircraft don't just have a minimum speed, they also have a maximum speed. And that maximum speed is limited by something called the speed of sound. As an aircraft approaches high speeds, especially near the speed of sound, the airflow around the wings changes dramatically. Shock waves begin to form, drag increases sharply, control becomes more difficult, structural stress increases, so now you have two limits: a minimum speed required to stay in the air, and a maximum speed you cannot exceed. At lower altitudes, there's a comfortable gap between these two speeds. Plenty of room to operate safely, but as you climb higher, that gap starts to shrink. The minimum speed increases because lift is harder to generate. The maximum speed decreases because the speed of sound becomes a limiting factor, and eventually, those two speeds get dangerously close. This region is known as coffin corner. It's one of the most critical limits in aviation, because in coffin corner, the aircraft has almost no margin for error. If it slows down slightly, it stalls. If it speeds up slightly, it risks structural damage or loss of control. There's only a narrow window of safe speed, and as altitude increases, that window becomes smaller and smaller until eventually it disappears, and that's one of the main reasons aircraft don't fly higher than 40,000 feet. But that's not the only reason, because engines also depend on air. Jet engines don't carry oxygen with them. They rely on the surrounding atmosphere. Air is pulled into the engine, compressed, mixed with fuel, and ignited. No air, no combustion, no thrust. At higher altitudes, where air is thinner, the engines receive less oxygen. That reduces their ability to generate thrust. So while the aircraft needs to fly faster to maintain lift, the engines are actually becoming weaker, producing less power. At some point, the engines simply can't provide enough thrust to keep the aircraft flying efficiently, and that creates another limit. Now add temperature into the equation. At high altitudes, temperatures are extremely low. This is actually beneficial for engines and aerodynamics because colder air is denser and improves performance. But again, it's a trade-off. Colder air helps, but thinner air hurts. So aircraft operate in a narrow band where the benefits outweigh the disadvantages. And that band is typically between 35,000 and 40,000 feet. Then there's the structure of the aircraft itself. Airliners are pressurized. Inside the cabin, the pressure is kept at a level that humans can tolerate comfortably. Outside, at 40,000 feet, the air pressure is extremely low, almost like a vacuum. That creates a massive pressure difference between the inside and outside of the aircraft, and that difference puts stress on the fuselage. The higher you go, the greater that pressure difference becomes. And beyond a certain point, the structure of the aircraft simply cannot handle it safely over long periods. So engineers design aircraft with specific altitude limits, not because they can't go higher, but because going higher would reduce safety margins. And safety is everything in aviation. There's also another critical factor: emergency situations. If something goes wrong at cruising altitude, like a loss of cabin pressure, the aircraft must descend quickly to a lower altitude where passengers can breathe safely. If the aircraft were flying too high, that descent would take longer, and time in that situation is critical. So altitude limits are also set to ensure that emergency procedures remain effective. All of these factors combine to create a very specific operating window: too low. And fuel efficiency suffers: too high, and the aircraft approaches physical limits. So pilots fly in that sweet spot, high enough to be efficient, low enough to be safe, and that's why most commercial flights cruise between 35,000 and 40,000 feet. But here's something interesting: some aircraft do go higher. Military jets, specialized reconnaissance planes, they can reach altitudes far beyond commercial airliners, but they are designed differently. They have different wing shapes, different engines, different mission requirements. They sacrifice passenger comfort for performance. Commercial airliners, on the other hand, are designed for reliability, efficiency, and safety. They operate within the limits that make sense for carrying hundreds of people across thousands of kilometers. So the next time you look out of that airplane window and feel like you've reached the top of the world, remember this: you're not at the highest point possible. You're at the highest point that makes sense, a carefully chosen altitude where physics, engineering, and safety all agree. Because in aviation, going higher isn't always better. Sometimes it's exactly where you stop. That makes flight possible.